In the previous episode, we explored magnitude-based hydrological signatures, which describe how much water a catchment produces. But quantity is only part of the story. Two catchments with similar mean annual runoff can exhibit completely different streamflow behavior. To understand these differences, we need another family of hydrological signatures known as variability-based hydrological signatures. In this video, we will introduce three widely used indicators that quantify streamflow variability and discuss their strengths, limitations, and applications in hydrological modeling. Stay with me. While magnitude-based signatures quantify the total amount of runoff generated by a catchment, variability-based hydrological signatures describes how fast and how much streamflow fluctuates over time. Their primary purpose is to characterize the temporal dynamics, flashiness, and regime stability of a catchment. These signatures provide valuable insight into watershed's storage capacity, attenuation characteristics, and drainage memory, revealing how rainfall inputs are transformed into streamflow responses. The three widely used variability signatures are as follows. First is the coefficient of variability, one of the most widely used statistical measures of relative variability. In hydrology, it quantifies variability of a stream flow relative to the mean flow, making it particularly useful for comparing variability across different catchments. An important point is that the coefficient of variation can be computed at different temporal scales. For example, a daily CV describes day-to-day variability, whereas an interannual CV measures how annual runoff changes over one year to another. These two metrics describe different aspects of hydrological behavior and should never be interpreted interchangeably. Its main strengths are its simplicity, dimensionless nature, and broad applicability for comparing catchments and assessing water supply reliability. However, it also has several limitations. CV can become unreliable for highly skewed, intermittent, or zero-inflated flow records, and a single CV value cannot distinguish whether variability is caused by floods, seasonal cycles, or droughts. It is also sensitive to record length and the selected period of analysis. The second indicator is Richards-Baker Flashiness Index, commonly abbreviated as RBI. RBI focuses specifically on frequency and rapidity of short-term fluctuations in daily streamflow. It measures catchment flashiness by quantifying day-to-day oscillations relative to the total streamflow volume. RBI is dimensionless and for a strictly non-negative flow series ranges from 0 for perfectly constant flow to a practical maximum of about 2. Its strengths include straightforward computation, intuitive interpretation, and strong sensitivity to changes in catchment imperviousness. Therefore, RBI has become one of the most widely used indicators for evaluating the effects of urbanization, land use change, and drainage modification. Its main limitation, on the other hand, is its dependence on the data's temporal resolution. Values calculated from daily records are not directly comparable with those calculated from sub-daily observations. RBI is also influenced by the selected period of record. Third is rate of change and reversal frequency. Developed as part of the Indicators of Hydrologic Alteration framework, these statistics describe how rapidly streamflow increases or decreases and how frequently the direction of flow change reverses. For a given daily discharge time series measured over time t, the daily change in discharge delta qt can be defined like this. Then, the mean rate of rise is calculated only over days where streamflow increases. It reflects how quickly a catchment responds to rainfall. High rate of rise values indicate a catchment with little attenuation capacity, typical of a small, steep, urbanized, or low permeability catchment where overland flow dominates. Low rates of rise reflect a strong groundwater or surface storage. The mean rate of fall, on the other hand, is calculated only over days where streamflow decreases, or delta Qt is negative. It represents drainage and evapotranspiration dynamics in the catchment. High values of rate of fall indicate rapid drawdown, while low values indicate a slow recession. Finally, the reversal frequency. It counts how often a streamflow switches between rising and falling conditions, making it particularly useful for identifying flow regulation and hydropeaking associated with dam operations. It counts the number of days the direction of flow change switches sign compared to the previous day. Abnormally high values are indicators of anthropogenic hydropeaking. Note that this group of indicators is sensitive to measurement noise and, like RBI, depends on the temporal resolution of the data. They should therefore always be interpreted alongside other hydrological signatures rather than in isolation. As a group, variability-based hydrological signatures provide a powerful description of stream flow dynamics. They are closely linked to the processes such as urbanization, reservoir operation, aquatic habitat disturbance, and drought stress. They are relatively straightforward to compute and often provide a strong statistical power for detecting genuine changes in catchment behavior over time. On the other hand, these signatures are sensitive to sampling interval, record length, and measurement noise. Furthermore, different indicators may respond differently to the same human intervention, meaning no single variability signature should be used as the sole indicator of hydrological alteration. Variability-based hydrological signatures have numerous applications in hydrology and water resources engineering. They are widely used in environmental flow assessment, detecting urbanization and land use change, catchment classification, model calibration and evaluation, and climate change impact assessment. Variability-based hydrological signatures help us understand how a stream flow behaves through time. By combining variability-based indicators, we gain a much richer understanding of catchment dynamics and hydrological response. In the next episode of this series, we will continue exploring hydrological signatures by introducing regime-based signatures, which describe the long-term seasonal characteristics of stream flow. Stay tuned.